In this video, we're going to talk about mass spring systems and how to find their period and angular frequency. To begin, we need to talk about the defining equation of simple harmonic motion. The defining equation of simple harmonic motion, if you remember, comes from the position equation, where we have x max is our amplitude, cosine is our function, the angular frequency omega times time is in the argument. And when we take the derivative, we get the velocity, which is going to be negative omega times x max sine omega t. And then when we take the derivative again to get the acceleration, we'll get negative angular frequency squared times x max cosine angular frequency times time. And what's special about this is that the x function is actually inside of the acceleration, and what we get is that the acceleration is equal to negative omega squared times x. This equation is the key to simple harmonic motion. And sometimes on test questions, you need to be able to recognize that this acceleration is the second derivative of position. And so if we want to write it in that form, we would say second derivative of position, which this is how you write second derivative of position, equals negative omega squared times x. So occasionally you need to be able to recognize or write this in. Now let's calculate the period and angular frequency for some systems. The most simple is a horizontal mass spring system. And this here asks us to demonstrate that this system is in simple harmonic motion and derive the angular frequency and period of the oscillations. So what we have here is an equilibrium position by this dotted line. And then we're going to stretch this spring some distance x to the right, and there will be a spring force going backwards to the left, which we can call Fs. When we release the box, it will oscillate back and forth. Let's look at a quick little animation to help us see this. Okay, so here I have the box on a spring, and if I stretch it away from equilibrium and I let go, then it's going to oscillate back and forth between the maximum positions to the right or to the left. One oscillation is going to start from one location coming to the back, so maybe the max, back to the max, that's an oscillation. Okay, so to demonstrate that this system is in simple harmonic motion, this is kind of an important clue that we need to do something special. And that something special is use the defining equation of simple harmonic motion. Occasionally, you'll be told to use Newton's second law to do this, but basically we're going to start with Newton's second law, that net force is equal to mass times acceleration. And then we're going to use that key, the acceleration equation that we just found, and also we're going to take advantage of what we know about the spring force. So the spring force is going to be equal to negative k times x. And the mass times acceleration, that key that we just used before, we might want to first say this, the second derivative of position with respect to time. That comes up a lot, but really what we want to do is we want to replace it with the negative omega squared times x. Doing this shows quite a few simplifications. First of all, the two negatives cancel, the position cancels, and what we're left with is the spring constant is equal to mass times angular frequency squared, and so the angular frequency is going to be the square root of the spring constant divided by the mass. So there, we've just found the angular frequency. And sometimes when you're asked to demonstrate that the system is simple harmonic motion, they just want you to plug in the second derivative to this equation. And so this is satisfying that first part of the problem. To find the period, we can take advantage of our period equation, which is that t is equal to 2 pi over omega, or omega is going to be 2 pi over t. And so when we plug in our equation for omega, let's do that to the top equation here, then what we're going to get is that the period is equal to 2 pi over square root spring constant over the mass. But that's kind of ugly. So instead what I'm going to do is I'm going to put the 2 pi out front and then reverse mass over spring constant here. And this is the period for a mass spring system, which we typically denote by putting an S in front of T. And if you are taking the AP Physics C mechanics test, then this is on the equation sheet, which is awesome. Okay, let's take a look at an example. A horizontal spring block system has mass m, spring constant k, and amplitude x max. A second system is set up with half the spring constant, half the mass, and twice the amplitude. Compare the second system's angular frequency, and maximum velocity to the original. Okay, so this seems like a lot of work, but really what it wants us to do is it wants us to say, okay, what's the equation for angular frequency? So angular frequency is k over m. And then it wants you to think about what would happen if you change these masses. So if we wanted to do that, we could maybe say angular frequency nu. Or another thing that sometimes people do is they call this angular frequency not 0, and then they write it like that. But I'm going to do nu because it makes a little bit more sense to me. Okay, so if I'm going to half the spring constant, then on top I'm not going to have k, but I'll have k over 2. And if I half the mass, then on bottom I'm not going to have m, I'm going to have m over 2. And then I double the amplitude. Well, the amplitude's not a part of this equation at all, so that doesn't change anything. And actually it works out that because we halved both the spring constant and the mass, then the new angular velocity is not changed. Angular frequency is not changed at all. So that's how they would compare. What about the maximum velocity of the original? Well, changing the amplitude did not change the angular frequency. But the maximum velocity, if you remember from a previous video, the maximum velocity, Vmax, is the amplitude of the velocity equation, which we derived earlier, so negative omega squared times x max. And if I'm going to twice spicy the amplitude, if I'm going to double it, then what's going to happen is that my nu, call this Vmax nu, that's a lot of writing there, it's going to have negative omega squared times 2 x max. And so it's pretty easy for me to see that, well, basically that maximum velocity is going to double because of that changing amplitude. But what's important to notice is that the angular frequency didn't change. And if I was going to write the velocity equation, which we can look at here, the velocity equation is not really going to change because the angular frequency is staying the same. And even if it was, it's not asking us about what happens to the velocity. It's asking about specifically what happens to that maximum velocity. And only x max is going to be affected by the amplitude. Okay, let's do a vertical system now. So in this particular system, you're going to have a spring that's hanging from rest, and then you put a box on it, and you're going to have a new equilibrium. So I'm going to write new EQ, a new equilibrium at that location. It's kind of hard to visualize this, so let's take a look at another animation to help us. Okay, so here we have a vertical hanging spring, and when we put a mass on it and we let it come to rest, it's going to stop at this new equilibrium position marked by this dotted line right here. Now I'm going to turn the damping or the friction off so that this spring will oscillate at the same amplitude each time. And now if we set a line for a new amplitude, then you will see that this system is just going to oscillate back and forth between that new amplitude that you set. But is the angular frequency going to be affected by this change in the length of the spring? Well, let's find out. To start, let's kind of define some variables here. We have this box, and it's going to have some mass mg going down. And when you stretch the spring a distance d so that it's at a new equilibrium, there's going to be a spring force acting up. And in this situation, when they're at rest, so we'll say at rest, then we can say that the spring force is equal to the weight mg. Now, the reason why that's important is because we know that the spring force is going to be the spring constant times the distance stretched, which we just defined as d. And so we can say K times d is the spring force, and it's equal to the weight. Now, because this equation came from us drawing a free body diagram, we don't need to worry about making it a negative kd, because the up and the down nature of the force vectors that we're drawing, they dictate what's going to be positive and negative in this. Okay, so this is going to be true even when the system is in simple harmonic motion. So Let's write that down. Simple harmonic motion. For simple harmonic motion, we're going to have to pull this spring down an extra distance, which let's call this distance y. That would be the amplitude, and we'll release the box, and it would go back and forth between these two lines right here. Okay, so when we write this equation, what we're going to want to do is we're going to say, okay, there are two forces acting on the box, just like before, mg and the spring force, but this time they're not balanced. They're not equal to each other because the box is accelerating. So we need to write a net force equation that ends in mass times acceleration. So we'll have mg be positive. The spring force is in the opposite direction. And we'll set that equal to mass times acceleration. So that's, Newton's second law. We're taking those two forces, setting them equal to ma. Okay, well, for the spring force, we can't use just d or just y. Instead, we have to use both of them combined because that's how far the spring is actually stretched from its equilibrium. So we'll have minus k d plus y equals ma. And then we're going to factor this negative in. So mg minus k times d minus k times y. And here's where something interesting happens. We already know that when the spring was at rest, we were able to relate d and the spring constant to mg. Now that is still true, and so we can replace mg with kd, because we're in Kentucky, ky. So anyway, when I get rid of these two kd's, they subtract, then what I'm left with is negative ky equals ma. Well, this is exactly like it was a horizontal mass spring system, and we ignored this distance d and all of this middle stuff. We didn't think about it at all. It's just stretched some distance y, and we're using k times y. So if we continue the solution, we're going to plug in our simple harmonic motion key for the acceleration. So here's how we demonstrate, boom, that this obeys simple harmonic motion. Of course, we've got a y instead of an x, so I should say y, and they will cancel out. These will become positive, and I'm going to get the spring constant equals m omega squared, which is the exact same thing as before. So the angular frequency is the square root of k over m. And then just like before, if we want to say the period, which I should probably put an s for these, the period is going to be 2 pi, and then we flip that, m over k. Okay, great. Well, that's awesome. If they're hanging vertically like this, it doesn't change anything about the angular frequency or the period. We might have to look at something when the spring is at rest to find a spring constant, because that is in our frequency and period equations, but otherwise we don't really need to overcomplicate things. So let's do two examples with vertical mass spring systems. A vertical mass spring system is made with two identical springs. When the springs are in parallel, the period is Tp, and when the springs are in series, the period is Ts. What is the ratio of Ts to Tp? Okay, so these problems are a little bit goofy, but they're really big on the AP test. So let's start by thinking about what this means. If you recall, when springs are in parallel, they look like this. Boom, boom, boom. They both connect to the box of mass that we're attaching to this. And when they're in parallel, the equation for their spring constant is very easy. You just simply add the spring constants together. Now I can call the spring constant k for each one because they're identical. And so right away I know that the parallel arrangement has a spring constant of 2k. Okay, so if I want to compare the periods, then I'm going to need to write what the period is. So period, we're in parallel, Tp. Got 2 pi times the mass of the box, which is going to be the same in both cases, over this spring constant here. So 2k. Okay, so that's in parallel. But in series is something different. If they're in series, then that means that the springs are attached to each other, like this. The equation for the spring constant, if they're in series, is a little bit different. The equation is going to be 1 over the spring constant, we'll call it ks in series, is equal to 1 over k plus 1 over k. And again, we're using k for both because they're identical springs. So finding the spring constant when they're in series is a little bit difficult. It takes another step. This is going to give us 2 over k. But I have to take the inverse of that. I've got to flip it so that I get k in series is actually equal to k over 2 as my final step. Now I can put this in my equation for period. We'll call this Ts. It's going to be 2 pi times the mass over the spring constant, but now the spring constant is k over 2. And what I would probably do is rewrite this and put the 2 just up on top right there. Okay, now ultimately, here, I'll make some room for it right here. It's going to ask me to do the series over the parallel. And I want to get a number, a fraction or a whole number, a ratio of the two. So what's going to be helpful is if I can take this new term that I've introduced, the 1/2 and the double, and just pull it out of the period equations. So what I mean by that, for this right here, I notice that I have a root 2 on the bottom. And so if I pull out 1 over root 2, then I'll have the ordinary period equation right there. Okay, so that's my TP. And if I do the same thing over here, then I pull this 2, that's a radical 2, out, 2 pi m over k. This will help me to relate the two periods because they're going to have the exact same thing in them. And when I write these next to each other, or I guess when I stack them on top, I'll put the series on top, so root 2 times 2 pi m over k. And on the bottom, I've got 1 over root 2 times 2 pi m over k. But all this stuff right here, it all goes away. And what I'm left with is root 2 over 1 over root 2, but really that's just bringing that root 2 up and squaring it. And so we're going to get 2 would be the ratio. You might technically say that the ratio is 2 to 1, and if it was a multiple choice question, you would see that listed. But that's how you find the ratio of these two periods. Okay, let's look at one more problem. Describe an experimental procedure that could be used to determine the acceleration due to gravity on a planet using only a meter stick, a stopwatch, and a mass spring system, but the mass is unknown. Okay, so this is an interesting problem, and it's kind of clever what you can do. So if I set up a vertical mass spring system just like this, and I use the period of the spring is going to be 2 pi m over k. I can see right away I don't know what the mass is m, so I'm going to have to somehow get rid of this inside of my period equation. So to do that, I'm going to take advantage of the fact that at rest, like before, I know that k times whatever the distance that it's stretched, I'm going to call it y, because it's vertical and it's going to stretch down, is equal to mg. And I can measure this y with a meter stick. Measure with meter stick. Okay, great. And if I want to, I can substitute this into my equation for k. So I'm going to rearrange this and get k equals mg over y. Then I'm going to plug that in here, and I'll get 2 pi times m over mg over y. But really that y is going to go up top here. And doing this is a really cool move. It cancels out the mass, and boom, I've got that the period, Ts, is equal to 2 pi times the square root of the distance that the spring has stretched y, which I can measure with a meter stick, and then also the period. Now the period, that you can measure with a stopwatch. So the procedure would be pretty simple. Measure the period of oscillation with a stopwatch, and measure the distance that the spring has stretched when it is relaxed. Now you could just plug those numbers in and get a value, and that might be a good experimental procedure to do that. But if you wanted to get a really accurate result, what you would do is you would say, okay, well, if I was to square both sides, if I squared this, I would get 2 squared 4 pi squared times y over g. Now what I want to get is g, and the things that I can measure are the period, boom, and y. And if I think of this as an equation that I could graph, then I would have basically 4 pi squared over g times y. And if I made a graph of the period squared versus y, then I should expect to get data that's going to be linear, and the slope of that graph is going to be 4 pi squared over g. And so to calculate a value for g, I would take 4 pi squared and divide that by the slope that I get from that graph. So a lot of questions, particularly on the AP test, they might ask you in some way to think about how can you turn this equation into some sort of experiment or something that you could graph. And this is definitely a good way to do it. Measure the periods, square them, and then measure the distance that it was stretched, and then go as far as you can. Okay, so this video is over.